Section 14.2, limits and continuity of functions of several variables. If you remember from single variable calculus, we would say the limit of f of x when x approaches to a exists and it's equal to, let's say L, if and only if the limit of the function as x approaches from left side is identical to what? The limit of the function when x approaches from right side. In other words, on a number line, either you approach to a this way or this way. There is no third way. However, that doesn't work for what? Limit of the two variable function, which happens to be a function of two variables, and the graph is a what? It's not a curve, it's a what? Surface in a space. For instance, the question is, how many ways can I approach what? To, let's say, a comma b, which is the limit of f of xy when x and y gets close to this point, a comma b. Well, there are infinite many ways you can approach to that point. So mayday, we have a problem. So this definition is out the door, because that only works if we have a single variable function and what? X is approaching to a either from left or right. Okay, if they match, the limit exists. If they don't, then we can go home. However, in what? Multivariable function, because your point could be in a space or on the floor, you can approach to that in infinite many ways. So we need to adopt a different way of doing the limit problems for functions of several variables. The classification of limit problems happens to be as follows. Some of them you can straight evaluate it, no problem, as if like you are substituting values for x and y, and lo and behold, the answer pops. The other kind of problems is you disprove the problem, meaning prove the limit doesn't exist. Okay. The last one, which is proving the limits, requires formal definition. And if you happen to see the formal definition of what proving limits in single variable using epsilon delta, then you know how this proof goes. However, for the sake of argument and the fact we are not required to do this, but if you're interested, let me know so I can, send you some handouts I have on proving. Specifically, if you're a math major, you really don't need this, you need to prove. So let me know which way you go on so I can accommodate. Let's do part A. Let's do classification of type 1, where you can straight evaluate. Okay, so in this case, what do we have? Limit of x minus xy plus 3 over x squared y plus 5 times xy minus what? Y cubed when xy gets close to 0, 1. So as x gets close to 0, 1, so anything with the what? X in it goes to 0 land, is that right? And y gets to get close to 1. So at the end of the day, that would be like 3 over negative 1, which is negative 3. So what does that mean? That means as xy gets closer and closer to 0, 1, right? Your z gets close to what? Negative 3. Okay, it just so happens this is your what? F of xy, correct? This is your f of xy, and that's exactly the same as what z is equal to. So that's what this is saying. Do you see it? On the other hand, what is the limit of what? F of xy, which is the square root of x squared plus y squared, as xy gets close to 3 comma negative 4. Well, that's kind of like what? 9 plus 16, which is square root of 25, which is 5. Once again, what does that mean? That means as xy as you get closer and closer to this point on the xy plane, 3 comma negative 4, the z value gets closer and closer to 5. So remember, this is not like evaluation of functions at a specific value of x and y, or as a specific point. These are limits. Remember, like for instance, in this case, neither x is equal to 3 nor y is equal to negative 4. They're just getting close to it. So the closer the point gets, what? You get close. The closer you get to this point, 3, negative 4, the closer the z gets close to what? 5. So then we have what? Still evaluation, but problem is when you kind of replace x's and y's with the value which x comma y gets close to, you get 0 over 0, which is undefined, correct? This is indeterminate form. Warning, L'Hopital's rule does not apply to multivariable functions. Sorry, guys. I know when you had this form in single variable, you took the derivative of the top, you took the derivative of the bottom, lo and behold, you took the limit, bang, you got the answer. Unfortunately, L'Hopital's rule does not apply for functions of what? Multivariable. So we have a problem. So what do? Well, in this case, try to manipulate the expression like on top. Did you know that guy factors like so? Okay, and remember x and y getting close to 1 and 1. Okay, remember x is not equal to y. Okay, that doesn't mean x is 1, y is 1. Okay, that means x and y get close to 1. All right. So because x is not equal to 1, so I can cancel these guys. So that would be the same as just finding the limit of x minus y as what? Xy gets close to what now? 1, 1, which is 1 minus 1, so it's 0. So I do have an answer. Do you see it? Okay. What about this guy? Well, x and y get close to 2, 2, but if you stick 2, 2 here, then again you get 0 over 0. Then again, L'Hopital's rule does not apply. Sorry to tell you guys. So what you have to do, once again, you have to manipulate. The only problem is I have a radical, so it's not a polynomial I can factor. So what do after I panic? I would rationalize the denominator. What does that mean? That means I would multiply top and bottom by conjugate of the bottom, like so. Do you see it? That's called conjugate of this guy. So when you do, you get x plus y. Don't forget, you still have to attach the limits as xy gets close to 2, 2. Don't drop the limit notation. So people know you are not dealing with algebraic problem, you're dealing with limit problem. Okay, so x plus y minus 4, what? Square root of x plus y plus 2. That's plus 2 outside of the radical, be careful. So there you go. All right, what do we get at the bottom? At the bottom, did you know this is like a minus b, a plus b? So that's difference of 2 squared. So the answer is a squared minus b squared, which is what? X plus y minus 4. There. A squared minus b squared. But what do you know? Remember, x plus y is not equal to 4. Okay, so what does that mean? That means I can wipe these guys out and get limit as xy gets close to 2, 2, what? Square root of x plus y plus 2. And when that happens, so I get what? Square root of 4 plus 2, which is 2 plus 2, which is 4. Do you see it? So that's how we do that. Sometimes you can use the squeeze theorem. Remember, this is also known as sandwich theorem from what? Single variable function, but is due to Mr. Gauss. That's also known as Gauss's theorem. You remember how it went. If G is trapped between fx and hx, x is what? Near a. So that means, let's say the limit of this guy as x approaches to a is not equal to a, is getting close to a, is L. So is the limit on the right side, h of x, as x approaches to a is L. Therefore, Mr. Gauss proved that what? The limit of the middle guy, which is trapped between these two guys, is also L. You know, this guy is L, that guy is L, this guy is in between, so that makes sense. This has to be approaching to L as x approaches to A. Sometimes you don't have a polynomial, nor you have a radical. You got combination of polynomial and trig function. How do you simplify this? Notice x and y gets close to 0, 0. If you stick 0 for x and y, you get 0 over 0. How do you manipulate this? So you use what? Squeeze theorem to find the answer, okay? So you and I, we both know x squared over x squared is 1. But the minute you add something like, let's say, 2y squared to the bottom, this guy gets what? Smaller than 1, right? Because remember, the greater the denominator, the smaller the fraction. Because all of these guys have powers of 2, so you know it's a positive number, but you know it's a fraction. It's less than 1 for all values of x, so this notation in the land of mathematics means for all, okay? Except 0, 0. Multiply both sides of this inequality by what you need, which is sine square of y. What I'm trying to do is go from here, the simple expression, all construct what I need as my original problem. So I multiply both top and bottom, both sides of this inequality, compound inequality, by sine squared. So this would be 0 times sine squared, which is 0. This guy would be just sine squared. But in the middle, I have exactly how the original problem looks like. Can you see it? You and I, we both know the limit of 0 is 0. The limit of sine squared y when y approaches to 0 is 0. So the limit on the left is 0, the limit on the right is 0. Well, guess what? The limit in the middle has to be 0 by squeeze or sandwich theorem. Do you see it? So now, how do you disprove? Remember, in single variable calculus, we said if the limit from the left side does not match the limit of the function when x approaches to a from right side, we say the limit doesn't exist. Once again, mayday, mayday, that concept doesn't apply for functions of several variables. For several variables, we need to select two paths or curves going through the point which x and y is approaching. Make sure the curve you select passing through this point produces two different limiting values, and those values have to be finite. Infinity, 0 over 0, they are not acceptable. They have to be numbers. Then the limit of f of xy as xy approaches to ab does not exist. Case in point, let's say we have this. Remember, the question is disprove. Disprove means what? Prove the limit, the limit does not exist. If you stick 0, 0, you get 0 over 0. And there is no way to manipulate this. There is no common factor. I'm very stuck with this problem. Luckily, I was told to disprove, not evaluate, correct? So what do I do? According to a procedure, I'm supposed to get two paths which goes through point 0, 0, which is the origin, on the x and y axis. So what are the possible paths? Well, possible paths, you can what? Get close to the what? 0, 0 along the x-axis, or you can get close to 0, 0 along the y-axis, or you can get close to 0, 0 along what? This is straight line. Remember, these are all curves, right? You can also get close to 0, 0 through this parabola. Notice all of these curves I'm graphing, they go through 0, 0. And how about this guy? You know, the cubic graph, that also goes through 0, 0. So the bottom line is you got to select a curve which goes through the point what the limit is getting close to. So if this was some random point A comma B, your curves had to go through that random point. In this case, that point is 0, 0. So all the curves you draw has to go through the origin. So anyways, let's try the y-axis. Let's try to get close to the 0, 0 via y-axis. So in y-axis, x is 0, but y is not 0, correct? So you take the limit, replace the x's with 0, correct? But y's a stay. But remember, y is not 0. It's a very, you know, that means it's what gets it's a small number, right? It gets close to 0. 0 divided by a small number is still 0. On the other hand, suppose we approach to 0, 0 via x-axis. Well, along the x-axis, y is 0, but x is not 0, correct? So what does that mean? That means go back to this expression, replace the y's with 0, but don't touch the x's. So when you do, the y goes to 0, but then that becomes limit of x squared over x squared when x approaches to 0. But if you simplify before you take the limit, x squared divides into x squared 1, so you get 1. Notice in both cases, I have a finite number. That's what this is, finite values. No infinities, no 0, 0, none of that. They have to come up to a number. So we say since 0 is not equal to 1, therefore the limit does not exist. Do you see it? So the selection of the curve is entirely up to you as long as the curve you selected goes through that point which xy gets close to. Okay, let's take a look at one more example. How about this guy? The limit of 6x cubed y over what? 2x to the 4 plus y to the 4 as xy gets close to 0, 0. Remember, it looks like the only type of disproof problems we do when the point gets close to what? 0, 0. That's not true. I mean, it could go close to some other points. But vast majority of the problems in this section, xy gets close to 0, 0. But that's not the only case, keep in mind. However, we have a problem here. If you go along the x-axis, y is 0, x is not 0. So replace the y's with 0, but x is not 0. This guy approaches to 0. On the other hand, if you go along the y-axis, x is 0, y is not 0. Replace the x's with 0, but don't touch the y's. But because y is not 0, 0 divided by a non-zero number, that's 0. So now we have a what? Match. So what does that mean? That doesn't mean the limit exists and it's equal to 0. In order for you to prove the limit, you have to examine infinite many possibilities. This is just two. You can't just take two paths and say because they look alike, therefore the limit is 0. That just means you didn't pick the right curve to disprove. So instead of along the x-axis and y-axis, or let's skip the y-axis, but instead of going via x-axis, or I should say a y-axis, let's select this guy. You know, y is equal to x guy. That's a curve which definitely goes through 0, 0. So what does that mean? That means go back to the original problem, replace all the y's with x's. Do you see it? Now take the limit as x approaches to 0. Notice I don't have y anymore because I replaced the y's with x's. So now this becomes a single variable function. That's why it's just x is getting close to 0. However, excuse me, this guy is limit of 6x to the 4 over combine the x to the 4s, 3x to the 4 X is not equal to 0, cancel these. So you get 6 over 3, which is 2. Once again, what does it say? It says because what? We selected two paths, namely, let's say either x-axis or y-axis, and y is equal to x. We did not come up with the same number. Remember, we're supposed to come up with a number. So since 2 is not equal to 0, once again, the limit doesn't exist. As far as the continuity of the function at a point, the definition is we say f of xy is continuous if the limit of x, y, as xy approaches to ab is exactly identical to the value of the function, that's the z component, when it's evaluated at ab. So if the limit matches the value of the function at a specific point, then we say what? The surface is continuous at that point. However, if this condition holds for every order pair in the domain of what? Z, okay, then we say the entire what? Surface is what? Continuous, provided this condition holds for every order pair in the domain of F. Do you see it? So the formal definition of what? Proving the limit is what? Limit exists, it has to do with epsilon delta. So if you have seen single function version of this, so this should be right up your alley. Otherwise, it would sound Greek to you. So in order to prove, we don't compute anything. We just have to find some relationship between some of the factors which what influences the limit. So here's the formal definition. Here it is. Let f be a function of two variables. Given small number epsilon, that's what this Greek letter is, very small positive number. We need to find another positive number called delta. So this is very small positive number. So this one is given, this we have to find, such that the difference between what? The function and its limit as small as epsilon, provided that xy lies in the domain of F, and the distance between xy and what? The point which is approaching is less than epsilon. Of course, distance has to be positive. What does that mean geometrically? Geometrically means I'll give you epsilon. Okay, so that means you suppose your limit's supposed to be within this interval, L minus epsilon, L plus epsilon. So you cannot go outside of that limit. You gotta be as close as epsilon to your limit. Okay, now my job is to find the disk in the domain of the function whose radius is delta and the center is AB. So any point I select in a disk, inside a disk with a radius delta, center at AB, will what? Map the function into this interval between what? L minus epsilon and L plus epsilon. Because we never said what epsilon is, we just said it's a positive number. So this idea holds true for every epsilon. Therefore, that proves. In other words, the job is, at the end of the day, you gotta find the relationship between delta, which is the radius of this disk, and the epsilon. Remember, epsilon is a given quantity. Delta is an unknown quantity, which we need to find it. So in other words, what that says in a different wording, if any small interval, like, this guy, is given around what? L, Then we can find a disk with center at AB, radius delta, such that F maps all the point in the disk except AB, of course, into that interval. And that would be like end of the proof. As I said, we are not going to worry about this, but if you are interested, you are a math major, please let me know so I can provide you with extra documents. Thank you.